Welcome Geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Let us now look at an example. Suppose we are given the matrix A equals to 6, -4, 3, -1, and we are required to find its eigenvalues and eigenvectors. The characteristic equation A minus lambda I equals to 0 yields 6, -4, 3, -1 minus lambda 0, 0 lambda equals to 0. And hence, when we simplify it, we have 6 minus lambda minus 4, 3, minus 1 minus lambda. And the next step is we are going to find the determinant of it. So the end result is lambda minus 6 times lambda plus 1 minus 4 times 3 equals to 0. And we will obtain lambda squared minus 5 lambda minus 6 plus 12 equals to 0. And simplifying this, we will obtain lambda equals to 2 or 3. When lambda equals to 2, we will have this matrix 4, -4, 3, -3 times x1, x2 equals to 0, 0. Thus, 4x1 plus 3x2 equals to 0 is the only independent equation in x1 and x2. It follows that any non-zero multiple of 3, -4 is a suitable solution to this equation. We choose x1 equals to 3, -4. Thus, the eigenvector for A corresponding to the eigenvalue of 2 is 3, -4. When lambda equals to 3, we will obtain this matrix 3, -4, 3, -4 times x1, x2 equals to 0, 0. Thus, 3 times x1 plus 3 times x2 equals to 0 is the only independent equation, which of course is equivalent to x1 plus x2 equals to 0. Any non-zero multiple of 1, -1 gives a suitable solution to this equation. We choose x2 equals to 1, -1. Thus, the eigenvector of A corresponding to the eigenvalue of 3 is 1, -1. We now consider the process of finding the eigenvalues and corresponding eigenvectors of a 3x3 matrix, which has 3 real and different eigenvalues. In the 3x3 example, A equals to -3, -14, -20, -1, -4, -8, 2, 8, and 13. Again, we wish to find when x is not 0, such that A minus lambda I times x equals to 0, the characteristic equation yields the determinant of this -3 lambda, -14 -20, -1 -4 lambda, -8, 2, 8, 13 minus lambda equals to 0. Now, we are going to find, using the determinant method, the roots, which are the lambdas. So, after solving it, we'll obtain lambda equals to 1, 2, and 3. Thus, the eigenvalues of A are 1, 2, and 3. When lambda equals to 1, we will have this matrix -4, -14, -20, -1, -5, -8, 2, 8, 12 times x1, x2, x3 equals to 0, 0, 0. Note that the eigenvector we seek has the following properties. -4, -1, 2 times x1, x2, x3 equals to 0. -14, -5, 8 times x1, x2, x3 equals to 0. And -20, -8, 12 times x1, x2, x3 equals to 0. And also x1, x2, x3 must not be 0. But each of the first three properties can be interpreted as requiring our desired vector to be perpendicular to each row vector of A minus lambda I. In this case, lambda equals to 1. Thus, our desired vector is parallel to the cross product of any two non-parallel rows. Remember, if you find the cross product of two parallel vectors, you will get the zero vector, which is of no use to us here. In this particular case, we are considering no two rows of A minus lambda I where lambda equals to 1 are parallel. Thus, we can find the eigenvector of A corresponding to the eigenvalue of 1 by finding the cross product of any two of the rows A minus lambda I, where lambda equals to 1. Choosing the first two rows gives x1 equals to 4, 1, -2, cross product with 14, 5, -8. And we will obtain 2, 4, 6. And simplifying it, our eigenvector is 1, 2, and 3. We must check that x1 is indeed perpendicular to the unused third row of A minus lambda I, where lambda equals to 1. So, -20, -18, 12, dot product with 1, 2, and 3, the third row, equals to -20 minus 16 plus 36, which equals to 0. The remaining two eigenvectors can be found using similar reasoning. The calculations are set up below. When lambda equals to 2, the matrix is -5, -14, -20, -1, -6, -8, 2, 8, and 11. Thus, the second eigenvector is the cross product of 5, 1, -2, and 7, 3, -4. And we obtain 2, 6, 8, which simplifies to 1, 3, and 4. And to check this, we perform the dot product. So, -20, -8, and 11, dot product with 1, 3, 4, we will get 0. When lambda equals to 3, the new matrix is -6, -14, -20, -1, -7, -8, 2, 8, and 10. Hence, the third eigenvector is 6, 1, -2 times 14, 7, -8. And we obtain 6, 20, and 28, which simplifies to 3, 10, 14. And we want to check it, so -20, -8, 10, dot with 3, 10, 14, and we obtain 0. So for the summary of results, when the matrix is 2 by 2, let's say 6, negative 4, 3, and negative 1, we have two eigenvalues, which are 2 and 3. And their corresponding eigenvectors are 3, negative 4, and 1, negative 1. For a 3 by 3 matrix that we have seen just now, the eigenvalues are 1, 2, 3, and these are the corresponding eigenvectors. You should now verify by matrix multiplication that in each case, AP equals to PD, where in the 2 by 2 case, P equals to 3, negative 4, 1, negative 1. D equals to 2, 0, 0, 3. And in the 3 by 3 case, P equals to 1, 2, 3, 1, 3, 4, 3, 10, 14. And D equals to 1, 0, 0, 0, 2, 0, and 0, 0, 3. Note that the columns of P are the eigenvectors of A in the order shown. Let us now take a look at this example. Given that the vector x is an eigenvector of the 3 by 3 matrix A with corresponding eigenvalue lambda, then if A is non-singular, lambda is not 0, and the vector x is an eigenvector of the inverse matrix A with corresponding eigenvalue lambda to the power of negative 1. Given that the vector x is an eigenvector of the 3 by 3 matrix A with corresponding eigenvalue lambda, and A is non-singular, then A minus lambda I equals to 0. Suppose lambda equals to 0, then the modulus of A equals to 0, which implies that A is singular. But A is non-singular. Therefore, lambda must not be 0. So we can write the characteristic equation now as AX equals to lambda x, and adding inverse matrix before on both right hand side and left hand side of the equation, we will obtain IX equals to lambda inverse AX. Hence, inverse AX equals to lambda to the power of negative 1 times x. So the vector x is an eigenvector of the matrix inverse A with the corresponding eigenvalue lambda to the power of negative 1. Next, we want to show that if x is an eigenvector of each of the matrices A and B with corresponding eigenvalues lambda and mu respectively, then x is an eigenvector of A plus B with an eigenvalue of lambda plus mu. So we have the matrix A plus B times x equals to AX plus BX, which also equals to lambda x plus mu x, since x is an eigenvector of each of the matrices A and B with corresponding eigenvalues lambda and mu respectively. And we factorize the x out, we have lambda plus mu times x Hence, x is an eigenvector of A plus B with an eigenvalue of lambda plus mu. Now, we want to show that if x is an eigenvector of each of the matrices A and B with corresponding eigenvalues lambda and mu respectively, then x is an eigenvector of AB with an eigenvalue of lambda mu. So we start with AB times x equals to A times bx, which is equals to A times mu x, since x is an eigenvector of B with corresponding eigenvalue mu. And so we take the mu out, so we have mu ax, and we know that ax is lambda x, since x is an eigenvector of A with corresponding eigenvalue lambda, which equals to lambda times mu times x. Hence, x is an eigenvector of AB with an eigenvalue of lambda mu. Next, we want to show that if x is an eigenvector of the matrix A with corresponding eigenvalue lambda, then x is an eigenvector of the matrix A plus ki with corresponding eigenvalue lambda plus k. So we have the matrix A plus ki times x equals to ax plus kix, and ax equals to lambda x, since x is an eigenvector of A with corresponding eigenvalue lambda, and equals to lambda plus k times x. Now, the square matrix A has lambda as an eigenvalue with corresponding eigenvector x. The non-singular matrix M is of the same order as A. Show that Mx is an eigenvector of the matrix B, where B equals to Ma M negative 1, and that lambda is the corresponding eigenvalue. The strategy here is revealed by writing down the equation which needs to be proved, which is Bmx equals to lambda mx. Post-multiplying both sides of the equations, b equals to ma m negative 1 by m yields the result bm equals to ma. Thus we obtain bmx equals to max and equals to m times lambda x, since x is an eigenvector of A with corresponding eigenvalue lambda. And we pull the lambda out and we have lambda mx. Finally, we want to prove that if lambda 1, lambda 2, lambda 3 are the eigenvalues of a 3 by 3 matrix A with corresponding eigenvectors e1, e2, e3, then AP equals to PD, where P is the matrix whose columns are e1, e2, e3, and D is the diagonal matrix shown below. So we start with AP equals to A times e1, e2, and e3, which simplifies to ae1, ae2, and ae3. And we know that ae1 is lambda 1e1, ae2 is lambda 2e2, and ae3 is lambda 3e3. But we can also rewrite them in terms of e1, e2, and e3. And P is e1, e2, and e3, So the first one equals to p times lambda 1, 0, 0. The second one is p times 0, lambda 2, 0. And the third one is p times 0, 0, lambda 3. Since each columns of the product AP is a linear combination of the columns of P, and hence equals to PD.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.